my name is Frédéric Simonis. I am one of the co-developers of preCICE. I'm mostly working on bringing remeshing to preCICE, at least again, which was a feature a long time ago. And yeah, so in this talk, I'll try to talk a bit about dynamic meshes in preCICE. So this is a very big umbrella term for many use cases, and I'm trying to point a bit at what you can use for these different use cases. So I'll try to focus at the beginning purely here on the user perspective. So yeah, dynamic meshes, there are different ways of handling this already inside preCICE. So a very common way is to use like ALE approaches, so where you have like a static reference domain and you use vertex displacement to morph this into some kind of physical domain. This is what we also support in many of the adapters, and it's pretty standard, right? And then there are other ways of handling this. That is, for example, with direct mesh access. So the basic principle is here that you that you directly access the static mesh on the participant that does something dynamic, and you essentially hide the dynamic problem from preCICE altogether, right? This is this has been done in various ways. Yeah, so the LuxDem people from Luc Besseron's group are a good example here. Yeah, Mercury FM and the DM, and yeah, so this is a standard way of doing this with particle codes, is that you access like the static mesh, and then you use just-in-time mappings to evaluate specific points of interest. So this is like a problem where you have very fluctuating mesh, and it doesn't really make sense to use remeshing, which you would have to tell preCICE how to handle that. The last part, which is also quite interesting, is so overset meshes, right? So here you have a second, so like a background mesh, foreground mesh, and there you anyway need to do a lot of manual labor in the adapter. So this is something preCICE can't do in most scenarios anyways. So here the solution is also to use direct mesh access. Access the mesh, and then most likely define your own mapping using the vertices, also the positions of the remote edge that you access. However, there are some occasions where you would like to still give this information to preCICE, and this here is just like a listing of those. So the first one is you have a code that does some kind of adaptive mesh refinement, and your code itself is coupled, and you have, for example, this adaptive mesh refinement on the coupling interface, and you would like to give this information to preCICE so that it can take advantage of this in the mapping methods, for example. Another example is also like changing meshes. So we had a good use case where you have like a growing mesh over time, where when specific points in time you add cells to the mesh, so your mesh grows. On the other hand, you can also have like a glacier or so where the mesh shrinks over time. Then there's also the option for especially ALE methods to do runtime remeshing if the solver supports that. So essentially, you read your data from your static mesh. At the beginning, you say, okay, does my current situation or my displacements lead to degenerate elements, for example, and then you can take the decision in your solver to remesh if this is somehow supported. Right. And the last part, this is very not obvious, but falls under the same category, and at least from the preCICE perspective, this is load balancing, right? So here, the mesh doesn't change whatsoever, but the partitioning changes. And the partitioning is tied to the different ranks on your solver. So essentially, your different ranks see different parts of your mesh. And if you want to use this together with preCICE, you need to tell preCICE what's going on. So this is also one of the use cases for this kind of remeshing inside preCICE. Yeah. So since version 3.2, you can enable these experimental features, in preCICE, and allow remeshing. As mentioned before, this constrains your configuration to a single parallel coupling scheme, which can also be implicit, more or less later. And this then looks like this in the API. So here we have a normal coupling loop, right? So you have your as long as coupling ongoing, you read data from your nodes, you do something with it, and you write your solution back, or something like this, and then call advanced. With remeshing, this looks a little bit different. Then you have something like this in the middle. So you would somehow evaluate if you need to remesh. This can be any criteria you can come up with. Then you would reset the mesh. So essentially, you tell preCICE, so preCICE in this case, this specific rank, please throw away my mesh M. Then you somehow do your remeshing. You get new positions that you can give again to preCICE. And then comes a very important part. This is this here. So now you're with the data that you read and the data and the spatial discretization that we have now are different, right? So you need some kind of remeshing and sort of remapping of your data. So from the original spatial discretization to the new one. Generally, you need this, and this is something that you have to handle in your adapter somehow. It is also possible that your solver supports this in some way, and this is super case dependent. Then after this, you continue as usual, right? You solve your system and so on, and you write your solution back to preCICE and continue as usual. And this is completely transparent on what happens in the background. So preCICE will handle this essentially without any other user intervention. This brings me to the implementation, where I try to also show you why, first of all, why we use this global flag approach, and why this is not always a good idea to use this, right? So let's look at the parallel scheme. In a parallel scheme, your solvers always run in parallel. So this is very easy to showcase here, right? Both call advanced at some point, then preCICE hands back over to the solvers, and they do this solve DT, which in practice is is a read solve write block, right? And then they call advance again. And what we'll discuss now is this one section here, so this repeating section of solve and advance. So what's happening is after after you write data to preCICE and call advance, in advance multiple things happen. So you have these map data parts which are partially optional. That depends where you decide in your configuration to run the mapping on. And you have this exchange part, which essentially just exchanges the information, right? So you give information to preCICE. preCICE needs to remap this from a local to a potentially remote spatial discretization, so mapping between meshes. Then you have the send, also the exchange between the different solvers, and then you need to potentially, or preCICE needs to potentially map information from the remote mesh to the local mesh that you then can read again from. So what happens now when one of these two essentially does a remeshing or changes the spatial discretization of one of these meshes on the fly? Quite a lot, actually. So you can see that this mapping is obviously out of date. The one big problem with this is that preCICE uses the mapping to figure out which ranks need to communicate with each other. So at that point, you cannot just recompute this locally, or you could, but at that point you don't know if you have all communication channels that are required to continue with the exchange later. Then also the exchange doesn't work because your local mesh may have changed, and if you need to exchange the information to a remote participant, then you run into the problem that the remote participant would think the spatial discretization is different. So you have a mesh disconnect here in information in the two participants. So these are all not nice things, and what we need is some kind of coordination, and this is where this global flag comes into play. And yeah, what I would like to do now is zoom a bit into this communication and try to explain a bit what we do here. So there are two kinds of handshakes that need to happen. So the preCICE API is designed in a way that is very simple to use from the outside, but that means that we have to do a lot of checking and communication internally. So first we have this so-called intra-coordination, and in this inter-coordination is a handshake between all the ranks of a single participant to figure out which ones have changed which mesh, because this is, you have essentially a case where this can be a mix and match thing. After this intra-coordination, all ranks know which meshes have changed locally. Then we need to know which meshes have changed remotely. That's why this inter-coordination part comes in. And this is one of the very expensive parts here. So your different participants need to communicate with each other here. So this is also kind of blocking. Yeah. And after this part, your local participant will do, again, some kind of scatter so that every rank knows now what's going on, if meshing is required and which meshes have changed. And if this is the case, then we have to go into something that we call like reinitialization. And what we do here is first we have to do something currently, because this is like the first kind of prototype that does this, is to essentially just completely close all secondary communications. So this are the communications between the different ranks of different participants, to get back to like a starting state that is clean. And then we need to do this repartitioning again. And the repartitioning is the part that is actually the most expensive part in your initialization. So in the repartitioning, we do some very expensive things, more on that later. And then at the end, we need to reset data that is specifically stored for your implicit coupling schemes. And this primarily affects historical data of quasi-Newton schemes, for example. Because again, the spatial discretization changes, so this doesn't match anymore. To zoom in into this repartitioning part here, we see that some things happen, and how these happen and in which order they happen and if they happen, this depends on configuration and so on. But in general, we exchange meshes, we compute the mapping, which we use for filtering to reduce the data, the amount of communication that we need later on. Yeah, and then we deduce communication channels, as I mentioned before, and we need to establish these communication channels again. Yes. And all of this needs to happen in here. So especially this mapping computation part can be very expensive. Yeah, so mesh filtering got way better, but the computational part is actually the biggest problem here. Depending on which system you are, also the opening these communication channels can also be pretty expensive if you have like a network file system or something like this with a lot of delay. Yeah, so this is essentially the implementation part. Now we come to some very basic examples. The first one is you've seen before in Maki's talk. We have this channel transport flow example, which is a super easy unidirectional coupling, right, from this to the flow over this step to like this convection diffusion problem where we start with this blob on the left-hand side. And this is a very nice example because we can use adaptive mesh refinement in the transport participant of this. Right. So this is a very toy example, but it is good to test the methods and so on. And this here is a case I developed together with Ishan Desai, which is actually super simple. So you essentially just here have a newest participant that remeshes, and here we also define connectivity information. So you can also use this for nearest projection mappings and so on. And this is a nice proof of concept. What we're currently also looking into is to create an open foam version of this, and also potentially use adaptive mesh refinement in there. So to have like a sandbox to come up with something, to have like a sandbox to develop the remeshing inside the open foam adapter. But this is still future work. Another case which is actually quite interesting, and I'm also trying to get for my dissertation, is the case by Jean-Marc Gatien, which presented this now a few years ago at a coupled in Crete. And what he is dealing with is this case here. So you have like an ocean bed, and he discretized this ocean bed in columns. These columns are then spread over different ampere ranks. And these columns consist out of different cells. So you have a Z-wise discretization here. And then these cells deform over time. They get squashed out. So essentially your cells in the column become zero thickness and essentially disappear. And what's also interesting here is that you have geometric events, geological events, where you deposit additional sands on top. So this is like a mixture of a shrinking and growing mesh case. And so, so he hacked around this, around our current implementation, or in the preCICE, and he's now trying to port this to the new version of preCICE to see if this works. Based on this, I have another toy example, which is actually very nice for scaling tests. So here we have the same, so an XY grid with a certain amount of cells, and we grow this in Z layers, so with time. And so some additional simplifications are that this is, so cells don't deform, cells don't disappear. This is a purely growing case. And we have matching meshes with bidirectional data exchange here. And this is also like a 3D volume coupling case that gets really expensive over time. So this is actually a very nice study case. At this point, I'm also going to say, if you have interesting examples here, contact me. I need some fancy things for my dissertation, and you probably also need a solution. And we can work together. Right? And this leads me to the summary. That yes, so this feature is available since version 3.0, which was released like in the 1st of April this year. Currently only works with a global configuration toggle for the aforementioned reasons. It only works for parallel coupling schemes. These can be explicit and implicit. Some further simplifications are that this currently only works for the very first time step in a time window. So essentially you need to make up your mind at the very start of your time window if you want to remesh or not. It also makes sense from a fixed point iteration point of view. And this is independent of rank and participant, as I mentioned also before. Some future work is to get this to work with serial coupling schemes, which is pretty complicated due to our current abstractions inside preCICE. Multi-participant coupling is both extremely challenging and very simple at the same time. So we have something that we call the multi-coupling scheme, which is essentially a parallel coupling scheme with multiple participants. This is very simple to translate to this scheme, and will probably be the next thing that will be supported. There's also the option to combine multiple coupling schemes and use these on different participants at the same time. And this is something that will most likely be very far in the future to get this running properly. Some other things that are on the nice-to-have list are like substeps after remeshing, right, which could be interesting for higher order time interpolation, and dynamic axis regions. And so this is both from the standpoint of changing your region of interest, as well as dealing with directly accessed mesh that is being remeshed. So these are still, in the work. And two very big problems here are also to remap past data. So especially critical is in implicit coupling schemes that you will lose the initial data of your coupling scheme, so also of your time window when you remesh in it, because that belongs to a different spatial discretization. So currently we discard that. So that's a bit tricky. And then another big one is how do you preserve the IQN history? Mapping from the old to the new spatial discretization sounds easy, but what schemes to use and so on. So this is a very big question. And that's it. So contact me if you have an interesting case or if you have questions.
Thanks for the nice talk. Are there any questions?
You can also just catch me in the coffee break. It's not a problem.
If not, then I would say thanks again